Can you hear me? Sorry, there's a bit of a problem with the net this internet this morning, the internet connection this morning. Let me try again. Okay. Okay, I can see the screen, but can you see the screen? And also, can you hear me? Okay, Jin Yong, thank you. I think let's get started. Before I continue with the rest of this topic of uncertainty management, any queries, any questions from the previous day's lecture? I'm trying to find the. Okay, so let's get started again. Okay, so we talk about certainty factors. Just a quick recap. So for example, if you see the sky is clear, then the forecast is sunny. But now with a certainty factor of 0.8, right? So then how do you calculate this? Because if the this is a condition, based on the condition that the sky is clear, right? Then the forecast is sunny. So you need to also consider that into the final certainty factor. So now, as I said before in the previous lecture, we when you multiply this together to calculate the final value that the forecast is sunny, it's only 0.4. Now from 0.4, you go back to your definition for the that value for the certainty factor of 0.4, you find that it's actually maybe. So finally, you find that the answer is that it is only maybe it is sunny. So it's not 0.8 anymore because of the sky is clear. So it's where we stop, I think on Wednesday. So now let's talk about the conjunctive rules. Now remember, conjunctive basically is here, if you look at it, it's basically the n function. So if you have not one, but more than one evidences, E1 to En, as shown here. So for example, you have your evidence E1, evidence E2, evidence E3, and evidence En. Then all these contribute towards strengthening your hypothesis that it is true with a certainty, with a certain amount of certainty factors, which is CF. So the certainty of your hypothesis H is established as follows, which is your certainty factor of H, given that evidence E1 and E2 and E3 and until En. Now, how do you calculate that? So you take the minimum. I think we have not covered this in the previous lecture, so this is something new. If you have this conjunctive rule, you have many evidence, right? Conjunctive. So it's an n function. You take the minimum certainty factor for each. So you have you take the, for example, if you have the certainty factor for evidence 1, E1, right? So imagine here, this is your evidence. So there are many evidences now, E1 and to En. So what you do is that you take the minimum of them. So this is written as this way: minimum certainty factor E1 of certainty factor E2, and then you compare all of them until En. Then you multiply against the certainty factor of your hypothesis CF, as shown over here. So for example, if the sky is clear, and now you can see here, this is an extension of the earlier example here. So this example earlier on talks about only the sky is clear. There's only one evidence, not many evidences. So here now we have more than one evidence, and it's actually they're all interrelated by So if the sky is clear and the forecast is sunny, then the action is, what do I do? The system tells you maybe you should, no, I won't say maybe, let's look at it, whether maybe or whatever it is, we'll see later on. So the action is, tell you recommendation, wear sunglasses with a certainty factor of 0.8, right? So this is the initial knowledge that we have. Now, then we're given that what's the certainty factor that the sky is clear? It's only 0.9, which is close to 1, quite high. And the certainty factor of your forecast is sunny over here, right? This is based on the weatherman, the radio or the TV telling you that the forecast is sunny, right? So actually, it is, I'm just forecasting, I'm estimating. So obviously, it is not 0.9 anymore. It's lesser than that because you are actually predicting. Whereas the first one, evidence is very clear in the sense that I can see the sky is clear. So there is 0.9, right? We can see. So what you call, I call it the sensors can detect that the sky is clear. So there is 0.9, whereas in the case of the forecast, it's only 0.7, right? So now if I ask you, without looking at the bottom here, what's the probability? How certain are you that I should wear sunglasses? Right, so you can see there's a bit of it's difficult for the expert to tell you exactly. So I think we talked about this in one of the earlier slides. The difficulty of the expert to actually consider the conditions involved and how this affects your final recommendation. So with these two additional evidences of certainty factor of 0.9 and 0.7, then we calculate this, right? As shown over here, how do you calculate? You calculate by taking the minimum of the evidences. And of course, if you sit down and look at it closely, you find that it makes sense, right? Because if I take the higher one, right? So to take the higher one, of course, the value will be different, but this is actually more of if you have this conjunction or conjunctive rule of the n function, you can see that it's always very conservative, as they say in English, conservative. You're a bit careful. You take the smaller of the lot. That's why you take minimum. You compare all of them and take the smallest one. So you're actually quite conservative, right? Because the smallest one will affect, right? The pull everybody down, right? So in this case, you have your certainty factor of sky is clear and of 0.9, and then the certainty factor of the forecast is sunny of sunny is 0.7. So you take the smaller one, which is 0.7. Then you multiply with your hypothesis certainty factor of 0.8 here, give you 0.56. Right, so this one is no longer. So you can see it actually brings it down to from 0.8 to 0.56 because of this other prior what you call it, prior evidences or conditions. Now, other than your conjunctive, we can also look at the disjunctive now. So what are the disjunction? What does disjunction represent? They represent the OR function. So for example, again, you have many evidences. So you have evidence E1 or until En. So when you actually apply the disjunctive rule, that is, if evidence E1 is true, or E2 is true, or En is true, right? Then your hypothesis H is true with a certainty factor of CF. So the certainty of the hypothesis now, the final, how certain are you based on these conditions, prior conditions of E1 until En is established as follows. So it is equals to, and then notice that the sign here, this represents disjunctive, which is basically a U sign. Or this is basically I call it the N sign. So this is your mathematical symbol for this conjunction, and this is your mathematical symbol for disjunction. So what do I do now? Early on, the conjunction, we use the minimum. So for the disjunction or disjunctive, we use the largest of the lot, meaning that you compare all the certainty factors of all the evidences. Your certainty factor E1, certainty factor E2 until certainty factor En, which is the largest value. Then you multiply against your certainty factor of your hypothesis H. So now let's look at an example. For example, the sky is overcast. Sorry, this is why I'm wondering what happened here. I think okay, you can see here.
Sir, are you not recording, sir?
Thank you. I forgot again.
Okay, it's okay, sir. No problem.
No, I should do it. I forgot. Sorry. In my excitement to get started.
Oh, okay.
Actually, it can happen anytime. Happen a few times. No, I forgot. Basically, good for reminding me. Yeah.
Okay.
I think it.
No problem,
Thank
sir.
you. Let me make a minute. So, minute. So I need to rewind back. Okay. Okay. Let's see, where am I? Okay. So we're here. Okay. Let's look at the conjunctive rules. So the conjunctive rules consist of many evidences now, other than E1. Now you have En. Then based on this conditional, based on the conditional evidence E1 until En, you have your hypothesis H is true with a certain factor of CF. So this certainty of the hypothesis H is true is established as follows. Means it calculated as follows. You take the minimum of the lot, minimum of the evidence E1 until En, the certainty factor of your E1 until En, and then you multiply with your hypothesis H, the certainty factor of the hypothesis H. So this is what you get. So example, if the sky is clear and the forecast is sunny, then the action is you wear sunglasses with a certainty factor of 0.8. Furthermore, you're given the certainty factors of your first condition. The sky is clear, is 0.9, and the certainty factor of your second evidence, which is forecast is sunny, is only 0.7. So therefore, when you calculate the final certain factor of your hypothesis H based on the condition of E1 and E2, right? And this is the symbol, the mathematical symbol for your conjunction or for your conjunctive rule, which is basically looks like an N. So you take the smallest of the lot of the certainty factors of all the evidences, which in this case is point C is actually 0.9 compared with 0.7. Clearly, it is 0.7, which is smaller, so therefore we pick 0.7, and then we multiply against your certainty factor of your hypothesis, which is 0.8, giving you a final answer of 0.56. Now this one then we also have the disjunction. Other than the conjunction, we can also have disjunctive rules. Let me just correct this. 1 minute. Let me just correct this. Okay. Oh, hang on. Okay. So this is actually okay. This should do it. Okay. No, it's not coming on yet. Just wait for a while. It's saving. Okay. That can see here, right? It's now corrected. So now the second set, which is your disjunction, using the disjunction function or your disjunctive rules. Now, what does the disjunctive rules consist of? Basically now, again, we have many different evidences, but in this case, because it's disjunction, so we use basically the OR function. Now, what happens when you have such disjunctive rules? What happens is that you take the largest of the lot, largest of the certainty factors of each of these evidences. Right. So again, this is more of a optimistic looking at things. The earlier one was a bit conservative, right? So you take the smallest, but in this case, when you consider the disjunctive rules, basically it's the or function. If the evidence E1 or E2 or E3, then you take the maximum of the lot. So for example, now, if the sky is overcast, the sky is no longer clear, the sky is overcast, this is your first evidence. And then the second one is all, the forecast is raining. So you can see here, of course, you can see it makes sense. So the sky is not very clear, not very sunny, and the forecast, the weather forecast from the radio station or from the TV says that it will rain, right? Forecast is rain. Then your action is what? Then you take your umbrella. Now, this one, again, remember, we always consider these rules, which is a knowledge based on the expert's opinion. So the experts say, in such circumstances, when you have such conditions, you take an umbrella. I will tell you that I'll give you the certainty factor value of 0.9. So therefore, and then the certainty of your sky overcast, which is your certainty factors, given as 0.6, and the certainty of the forecast of rain is actually 0.8. So there are two values, additional values based on the conditions, so it's 0.8. Then when you calculate your final certainty of your hypothesis H, right, based on these conditions that E1 or E2 is true. And notice that in this case, the E1, E2 are no longer 1. They are actually some other value less than equals to 1. So the first one is 0.6, second one is 0.8. So the largest of the two will be 0.8. Then you multiply against your final hypothesis, which is 0.9. So you get your 0.72. So it's still quite high, but basically it's not the same as before if it's not based on any conditions, right? So when the same consequent, now consequent, just to remind you, consequent is the other part, the action part, the then part. The consequent is when the same consequence obtained as a result of execution of two or more rules, the individual certainty, right? So you can see, I'll show here what it means. The individual certainty factors of these values, of these rules, more than one rule, must be merged, right? To give a combined certainty factor for that hypothesis. So for example, if your knowledge base consists of two rules now, the first rule says that if A is X, right? Again, this is your, with a certainty factor involved, right? And then C is Z. C is Z with a certainty factor of 0.8. This is one rule. The second rule is that if B is Y, so the final consequent, right? But it's what it means. It's the same consequent. Notice that it's the same consequent. That means that I still have C equals to Z. The C is Z, but with a certainty factor of 0.6. This is based on the condition that B is true, B is Y. So notice here, they both you have the same consequent, which is C is Z, but the initial conditions that contribute, or initial evidence that contribute towards this final consequent is not the same. So when A is X, it also contributes towards C. So is B is Y, also contributes towards C. Now, what certainty should be assigned to object C having value Z? So in this case, you can see rule 1, Z is C is Z, certainty factor 0.8. Second one is C is Z 0.6. Assuming that both of these are fired, that means that you still see A is Z, A is X, and you still see B is Y. If I can do this, okay, you can see here A, right, is X, and then you have your B is Y. And both of these contribute towards C is Z. So how do you calculate this? How do you calculate the final consequent of C is Z? What is the actual value here? So let's look at it the next few pages. Now, common sense again suggests that if we have two pieces of evidence, that is your A is X, that is your evidence, and B is Y, and from different sources, right? So this is not the same as before, because if you are upon the same source, you can maybe use either the conjunction or the disjunction function. But in this case, they are from two different sources. Therefore, because the rule one may or may not fire, regardless of it's not dependent on rule number two. Rule number two from a different sensor, right? I always call it different sensor. So your rule one from different sensor and your rule two from different sensor. So your rule one can fire or not fire regardless of what happens to rule number two. So they are independent, right? From different sources. So as a result, you have two different rules from different sources. But they both support the same hypothesis. This is your C is Z. No, therefore, in a way, your common sense will tell you that since you have more than one rule firing, and they both support the final conclusion, so this hypothesis, which is C is Z, should increase. Right? Common sense tells you that. Again, then for me, I will question, what does this common sense do with this? Again, because always remember, what are we doing here? We are trying to build an artificial system based on a human intelligence. So humans have this common sense. So we also need to include such common sense into the system itself, even though it's artificial. So to build a stronger and more intelligent system. So this, therefore, as a result of two rules now firing, although they're from different sources, the confidence in this hypothesis, that means that the strength of this hypothesis should increase because I have two rules now firing. If it's only one rule, right? So depending on what's the value here, what the CF for A is X, so this will actually contribute. But since you have two rules firing, it should increase your confidence in this hypothesis that C is Z, and therefore become stronger than if only one piece of evidence had been obtained. So we can always play with this, combine this. I think we will look at this in more detail in the next slide. So to calculate the combined certainty factor, we can use the following equation. So this is divided into three parts. So this is when you have this combination of certainty factors from two independent rules, which is your CF1 and CF2. Now, then the final value will be CF plus CF2 multiplied by 1 minus CF1. That is only if both your CF1 and CF2 are positive values, more than zero. On the other hand, if either of these values, either your CF1 is less than 0 or your CF2 is less than, one of them is negative, right? So you can have here negative. You take this, you use this particular formula. I've also uploaded another 2 pages of the explanation to the earlier measure of belief and measure of disbelief, which we didn't have the time to discuss in the earlier lecture. So please look at that. Now, so you will see that we use a lot of these functions here. Now, so in this case, if either one is negative, your CF1 and CF2 is negative. Remember, we discussed this before. The range of your values of the CF1 and CF2 is what? It can be -1 until +1. So it can be negative. That is your CF certainty factors. So if either of them is negative, so you use this formula to calculate. I believe this formula is actually given in your the exam. Is a part of the list of equations given to you. Now, what happens if both of them are less than both of them are negative? Your CF1 and CF2 are negative, so you use this particular formula, right? So so what is this CF1 and CF2? Now, CF1 is the confidence or your certainty factor of your hypothesis H established by rule 1. So your CF1 is based on your final hypothesis based on rule 1. Now, CF2 is the same thing, but now this was established by rule 2. And then here, right, of course, if either of them are negative, that means your CF1 or your CF2 are negative, either one of them, you take the absolute magnitude, that means the value, ignore the sign. So it's minus 0.3 was compared to positive 0.2, right? So you should take minus 0.3 or minus 0.3 as the actual value because it is smaller than. So you take you take only the magnitude here. You take so either one. So let's say minus 0.3 here, CF1, and CF2 is positive 0.2. So value will be what? You take 0.3, right? So it's 1 minus 0.3. You don't 1 plus, right? 1 plus 1 minus 0.3. Follow? So this is actually taking the magnitude of that value. So we'll be careful with this. So you can see here it's only the magnitude. So you convert that minus 0.3 into just positive 0.3. So it's basically compare minus, sorry, my mistake, minus 0.3 versus 0.2. So you take the 0.2. Now, what happens the other side? If you have this is CF2 is minus 0.3 and then CF1 is 0.2. So you still take the larger of the two. Now, what happens if you have minus 0.2 and your positive 0.3? So you take the smaller of the magnitude of this either of these values. Now, note that in some books, the first part here, for example, the first part here, the equations are stated in a different way. You can have CF1 plus CF2 minus CF1 times CF2. Right, so you can see here, so you have your CF, so you have your CF1 plus CF2 minus, so you have your, right. So this one applies to the top here. So you can see here, if I expand this out, so I have a CF1 plus CF2 minus CF1 times CF2, which is same as this. Some books put it in a different way, but they actually mean the same thing. So again, this one actually, so it will be CF1 plus CF2 plus CF1 CF2. So the last one here is actually plus. So this in some books they actually show the equation differently, but you can see that actually they are the same. So I've actually combined them to show it to you in a table form. So you can see here, if the either one, either your, what do you call it, your, in this case, the one in yellow, you find that your CF1 is negative, but your CF2 is positive. So you use back the same formula here. And then you have your, on the other hand, you can have a CF2 non-negative, but CF1 is positive. So either one is positive, which is represented in the yellow boxes. Otherwise, you use the formula shown here. So it's basically just you have to know how to use the formulas. So now let's, for example, your CF1 and your CF2.
Sir, sorry, can you explain
Yes,
again
please.
for the
Which one?
middle one? You say take minimum of what?
This one is it?
Previous
Or before
slide.
this?
Yes.
This one?
The
Yes,
middle one,
here.
yes.
Okay.
You
Okay,
say
let's say,
the CF1 and CF2
Yep.
in the bracket one, the modulus one, you choose the minimum of the
Magnitude.
magnitude. So mean to say like CF1, the range choose the lower range of the CF1 and then CF2 also.
Okay, correct. Let's see. Let's say, okay, let's say now if you have, okay, first condition is that either one is negative. Okay, either one. So it's not both. Both you use this one. If both of them are negative, you use this particular formula over here. Now, if your, let's take one example, which is your CF1 is minus 0.2, right? And then your CF2 is actually say 0.3, right? So if you take the magnitude, you will be comparing 0.2 compare against 0.3. You take the magnitude. So the smaller of the two will be 0.2. So this denominator, finally you get 0.8. Right, so you have, so in this case, so the top one will be, top one is a bit different. So top one will be minus 0.2 plus 0.3, which gives you 0.1. So the value, the final value of this will be positive 108, which is 0.125, if I'm not mistaken. Right, so this is what it means. Let me just right. So let's look at one example here. Now your CF2 is 0.65. So you have your first case. Go back. This is 0.65, 0.2. So you have your maybe you can look at it here. This is 0.65. This is 0.2. So your CF2 minus 0.2 over here, correct? Over here now minus 0.3 and 0.45. So this one will be minus 0.30 and your 0.65. Oh, sorry, 0.445. This is actually 45. Let me just erase this. Oops. 0.45. So if I take the first case, that means that both the CFs are positive. So I have your 0.65 over here, and then your 0.45 over here. So you substitute this inside. So this will be this is CF1. CF1 with 0.45. So this will be 0.45 plus your CF2 is 0.65 multiplied by 1 minus CF1, which is 0.55. So 0.55 multiplied by 0.65, and then you add on to 0.45. Basically, it is strengthening it. So, and that's how you solve the rest. So let's look at this. Oh, okay. I think this one. Okay, so this will give you 0.8075. Right, so to give you 0. So can someone punch in the numbers? 0.65 multiplied by 0.55. So what is that? 0.65 multiplied by 0.55. What do I get? Should be 8075. So it should be 4075, I believe. So this should be 0.40. Oh, sorry, not 4. 4 maybe 4475. Is it 4075? Correct. 4075. 8075. So 4075. Which is 5. 8. So it's 3575. So it should be 3575. Correct. 3575. Jingwei, thank you. So it's 3575. That's how you get. Now, the same applies here. So you have in this case, you have your CF1, which is minus 0.35, right? Then you multiply with your CF2 is minus 0.2. So both are negative. You can see here, minus 0.2. Sorry. This is CF2, correct? CF2, 0.2. CF1 is multiplied by 1 plus CF1. CF1 is, okay, 1. So it's actually minus 0.35. So it should be 0.2 give you 0.2 into what? Into 0.65. Right? Because your 1 minus 0.35 becomes 0.65. So 0.2 of that will be, then you minus this. So you should get 0.44 minus 0.44. So basically, you can see here actually, because of the CF, both are negative, right? So you have your, right? So you can see here, both negative. So actually strengthen the negative certainty factors of either CF2 or CF1 when they combine, right? Now, when both are positive, that's what it's saying over here as well, right? Here, strengthen, right? Become stronger, right? So you can see here, see here, so over here, strengthen. Now over here, if one of them is not the same, that means that one of them actually is negative, right? And this is positive. So positive and negative actually will decreases it, and the same applies here. Positive, negative. See here, right? So this actually decreases your positive certainty factor 1. Same applies here. So this one minus 0.3. So this will decrease your final certainty factor instead of increasing it. So, but if both are positive, as shown here, it will strengthen. Same applies here. So this will become more negative. This will become more positive compared to 0.65 and 0.45, and minus 0.2 versus and also minus 0.3. So it actually becomes more negative. So, but if either one is actually negative, it will bring down the positive one. Right? Is what it shows. So the certainty factors theory, I think now we're coming to the end, towards the conclusion, provides a practical alternative to your Bayesian reasoning. So this is a practical alternative, but you still have to depend on your seeking the advice of your expert. Now, the heuristic manner of combining the certainty factors is different from the manner in which they will be combined if they were just probabilities. So the downside is that the criticism is that the certainty factor theory is not mathematically pure, but it does imitate, follow the thinking process of a human expert. That's why we talk about the common sense. So this is the way human experts think, right? So if you have, so it helps you to create a more alternative way of reasoning based on your data, right? Other than your Bayesian. Bayesian has some limitations, but that's why we have this what do you call it? This certainty factor theory. So now when we want to compare the two methods which we have studied so far for expert systems, which is first of all your Bayesian reasoning, and then the next one is your certainty factors. Probability theory is the oldest and best established technique to deal with inexact knowledge. It means you cannot get something which is very exact. And then also we also deal with your random data. So this is when you're faced with inexact knowledge and your random data, how do you try to find a way, find the answer when you have such knowledge? So the probability theory works well in such areas as forecasting and planning, when the statistical data is usually available. So when you have historical data, right, tell you that on such a day, the chances of rain is this. So you have such statistical data, and accurate probability statements can be made based on sufficiently large amount of data collected. So these are the two foundation, right, to actually support why probability theory works, provided you have sufficient historical data, right? So you can then make such probability. However, in many areas of possible applications of expert systems, such reliable statistical information is not available, or we cannot assume the conditional independence of the evidence. So there are two factors here. First is we do not get your statistical information. And then secondly, you suspect the evidences themselves are not independent. That means that something else will influence it. Something else is influencing, so therefore you cannot guarantee the conditional independence of your evidence. So as a result, many researchers have found that the Bayesian method is not suitable because the Bayesian is based on probability theory. So as a result, it is found that your Bayesian method is not suitable to be used for such work. So as a result of such dissatisfaction, it has motivated the development of your certainty factors theory. So certainty factors is to overcome these problems of insufficient or unreliable statistical information, and you cannot, and also the conditional independence of evidence is questionable. Now, but the downside is that the certainty factors method approach lacks the mathematical correctness of the probability theory. It outperforms your subjective Bayesian reasoning in such areas as diagnostics. So in areas when you use Bayesian, you will find that your certainty factors method produce more accurate results than your Bayesian reasoning. So certainty factors are used in cases where the probabilities are not known. So if you cannot find the historical data to give you the probability of such an event being true or false, or are too difficult or expensive to obtain. Now, what do you mean by that? So for you to collect the data, you need to talk to, let's say, 1,000 or 10,000 people, right? So it's difficult to talk to 10,000 people to ask them for their opinion. As an example of what do you mean by difficult? Expensive, the same thing applies, right? If you want to talk to people to collect their opinion, right, you still need to pay people to go out and talk to 10,000 people or 1,000 people. So that's also expensive, right? So I'm just giving you some idea. What do you mean by that? Now, based on the this evidential reasoning mechanism, right? The evidential reasoning mechanism can manage incrementally acquired evidences. So we can this uncertainty management method based on evidential reasoning, right? Can manage incrementally acquired evidence. That means that you can actually at some point you increase the evidence incrementally. And then the conjunction and disjunction of hypothesis. That means that I can also combine the different evidences to contribute towards my hypothesis, either through conjunction or disjunction, as well as evidences with different degrees of belief. Right? We talked before, which is a measurement of belief and a measurement of disbelief. So finally, the certainty factors approach also provides better explanations of the control flow through a rule-based expert system. So this one actually in favor that the certain factors have this advantage, that is provides better explanations how you arrive at your final answer. Now, the Bayesian method is likely to be most appropriate. So when can you use the Bayesian method? You can use the Bayesian method if reliable statistical data exists, and the knowledge engineer is able to lead, and the expert is available for serious decision analytical conversations. So one of the things is that if you want to use the Bayesian, make sure that the domain expert is able to have the time to talk to you, to discuss, to share his or her views of the outcome of such certain rules. In the absence of any of the specified conditions, the Bayesian approach might be too arbitrary and even biased to produce meaningful results. The Bayesian belief propagation is of exponential complexity. So you can see what we're saying is that it doesn't increase linearly, but it increases exponentially. And therefore, if your system requires a lot of rules, a large knowledge basis is not practical. Therefore, it's impractical for large knowledge bases. So I've actually summarized what I've said so far into this table, right? For you have a quick reference. So the strength is that for Bayesian, it works well when reliable data is available. Weakness is that it is not practical if you have a large number of rules, which means that your knowledge base is large. On the other hand, if you compare the certain factors, it works well for incomplete data. It provides also better explanation of the results, but on the other hand, the downside is that it lacks mathematical correctness. It's just basically it just seeks the human sort of common sense. Now, with the Bayesian method, there are also too many probabilities required, and most of them could be unknown because you need a lot of probabilities for certain evidences. So, but can you get those data? The probability of this happening it's not that easy. So that's why Bayesian won't work very well. That's one of the difficulties there. So recapping, what have we learned in this particular topic? Topic number 4. So we talk about uncertainty, where the information, the data itself is may not be complete, missing due to various reasons. We also do a quick revisit of the probability theory. What you mean by probability of an event happening, right? Of a tail when you toss a coin, when you toss a dice, for gaming purposes. Then we introduce the Bayesian reasoning, and we look at some of the weaknesses of your Bayesian reasoning, which is your biasness of the Bayesian method. So therefore, that introduces us to certainty factors as a alternative to your Bayesian method. And then this one also is part of the certainty factors, and this one is based on what we call evidential, from the word evidence reasoning. Based on evidence, this is your conclusion. Okay, so we come to the end of this particular topic 4. We shall take a 5-minute break, and then we come back to start a new topic on fuzzy logic. As usual, before I stop, are there any questions that you need to ask?
So I want to ask, just now you say one of the weakness of the certainty factor is it lacks mathematical correctness, right? Like how, like compared to the Bayesian, or like how much does it lack? Because this one you need to like I mean like there's more calculation since if you combine different two different certainty factors. Basically, it mathematically speaking, like there's a bit more calculation compared to the Bayesian, which plug in formula one.
Correct.
So yeah,
I reckon they're not talking about this calculation. I think they reckon they're talking about the, you see, your Bayesian, the foundation is based on statistics. That means that what is the probability that it will rain, right? But on the other hand, the certainty factors theory is based on your estimate. That this is what's your estimate of your, it's not based on probability, right? That's why you see the top here. Because if you this is actually incomplete data, so as a result, incomplete data, you still make a guess. What is the certainty? What is the certainty? I think that's why they didn't use the word probability. If you ask me, in a way, your certainty factor is actually in a sense a probability, isn't it? What's the chance that you are sure of this happening? So it's actually a measurement of your confidence rather than the probability. So that's why I think that's why they say it's mathematical correctness. If you go back.
So basically this one is kind of like a guessing, while the Bayesian probability is based on like a previous data
probability
kind of thing like that.
Correct. So it's actually based on that.
Okay.
But you see, I mean, if I'm on this side of the table, I don't believe in certain factors theory. For example, I would say that your certain factor is not based on but based on solid statistics. statistics in a way, because if you can accumulate over time, I can have pretty accurate. I think that's why some of us believe that, for example, in the UK, their weather forecast can be quite accurate. So I heard from my friends that before they go out, they check the radio forecast. So should I bring my warm clothing, because especially during the winter months, or the start in between, when it can become very cold. So they say, do I bring my extra clothing because it can get cold? So they believe in that, because why? They've been collecting a lot of data, many years of data. So that is provides you with pretty solid evidence that pretty accurate. But in the case of the certain factors, because such data is not available, so it's actually based on your expert opinion. But expert opinion, we also said before, the expert opinion. If I say, what's the chance of what should I bring my sunglasses today because it's pretty sunny, right? So if you ask that statement to the expert, he or she can tell you exactly with a certain value. But I think what we discussed so far is that the expert, when you say, oh, this is actually what happens if should I bring my sunglasses today, based on the condition that the sky is sunny. So that one actually for humans, you find that it's not easy for us to base your judgment based on certain prior condition. So this is what we're saying. So this is actually not based on the just one event, but event on something happening before this event that contributes towards the event. So you can see that that's why it's a bit difficult for experts to actually give you that. But to overcome that, actually we have all these mathematical equations to actually avoid that. So we still ask the expert to give you on one event happening, what's the chance of that happening. But when we combine it, you see over here, what I want you to show is this. Here, for example, so if you say, ask the expert, should I wear sunglasses today? Today, wear sunglasses based on my judgment is 0.8 certain factor. But you see here, you have other two conditions. So this condition of sky is clear is actually given by the evidence, and it said 0.9. So this has nothing to do with wearing sunglasses. So when we combine all these three, you find that the actual action, or rather say recommendation. Remember, when we started doing this, we talked about 5 different ways we can use the output of this system: recommendation, heuristics, strategy, right, and a few others. So you can see here, as a result of these evidences, this has reduced. Now, how did this come about? Why is it reduced? Why do I straight away use 0.56? Because this value is given by the expert based on just that, if you like, that particular event happening, right? But so you ask them, sky is clear. What's the chance of sky is clear today? It's 0.9. So you can see the sky is clear. So evidence is 0.9. Forecast is sunny. How reliable is that? 0.7. So when you combine all these prior conditions, right? Should I wear glasses today, given that the sky is clear and the forecast is sunny? So this is your prior conditions before happening. So this is what is basically trying to say, right? So I think we also talked about this before. The expert is cannot give you a really pure what you call estimate of the event. That's why we have this this theory, this method of overcoming it. Okay. Good. Anything else?
That's all, sir.
I'm still here. You can ask if you want to later on, or maybe not. So let me stop here, and then I will prepare for the next lecture, which is 5 minutes from now. Okay. So take a short break.
Sir.
Yes.
Sir, can I ask about the assignment grouping?
Yes.
Because I registered a long time ago, but my name is in the no team member list.
Not in the what?
Yeah, you got a list, right? The no team member identified, right? Yeah. My name is there, but I registered a long time ago with my friend.
Hey, but if your name is there, maybe I'll check again. Let me see. Who is that? Jing what?
Jing Hui.
Jing Hui.
Number 7.
Surname?
Huh? Tan Jing Hui.
Let me check again. If you remember, okay, I can check. I can give me a minute. I can check. Zhang Ting Hui. Okay, it's okay. If you remember, it's okay. I will check back. Right? Maybe the system, because if your name is there, I should be able to find it. Right? The rest of you, please, get your members sign up, and then we will complete this exercise. And then I think because some of your, I think, okay, this your E or MH. Jing Hui.
MH.
Okay, let me check MH. Because I think MH. Okay, there's I think there's one student not here, so it should be 39 of you. So I think it makes sense to have 3 of you, one group of 3. The rest should be 2. Okay, let me just check on that. Jing Hui, thank you. Okay, rest of you take a break and then we'll come back. Jing Hui, are you still there?
Yes, sir.
Confirm, because when you key in your name, you've actually included extra space. So my Excel cannot detect that. So it's confirmed. You have a partner. I think one, isn't it?
Yeah.
Thank you.
Okay.
Okay, we will start shortly. Okay, so now we start a new topic, which is Introduction to Fuzzy Logic. And you see there are certain similarities between the fuzzy logic and what we studied so far in the earlier two topics of expert systems. So what is the learning outcome? What do you hope to learn from this after completing this particular topic? So there are 5 main points here. We look at basically introduction, or what is fuzzy thinking. Then we also spend some time to look at the fuzzy sets. What are the fuzzy sets? So these are the fundamentals of your fuzzy logic system. So we look at your fuzzy sets. Then we move on to I will say this is your key strength, key advantage, key differentiation of your fuzzy logic systems, which is your linguistic variables and hedges. You find that because of these linguistic variables, unlike the other more complex or equally powerful or more powerful methods in AI, this is one of the strengths of your fuzzy logic, because we can read it like a book. It's that clear, right? We can follow how you arrive at that particular conclusion. Then we look at the operations of your fuzzy sets. How do these fuzzy sets operate, and how do you compute the value from them? Then lastly, we will conclude with some of the fuzzy rules, the fuzzy rules that we have actually created, and see how they work. So let's jump straight to what is fuzzy thinking. Now again, you see that such intelligent systems based on fuzzy logic or fuzzy thinking, again, base it back to the experts. So the experts rely on common sense when they solve problems. You don't try to use something too complicated. You just use common sense, and that is experts use when they solve problems. And again, you can see one of the key point here. At the end of the day, we are using fuzzy logic systems to solve problems. I mean, for some of us, that's what engineers and scientists do. We are trying to solve problems. We're not there to do anything else but to solve problems. So we need all these tools to help us to solve problems. So we are using these fuzzy logic systems as a tool to solve problems. And then because they're based on human intelligence, so that's why we base it on the human experts who uses common sense to solve the problems. So then question is, how can we represent the expert knowledge that uses such vague and ambiguous terms in a computer? Now I can see, I think since we just completed the topic on the uncertainty management and also Bayesian reasoning, you can see that unlike the earlier two methods, now we are trying to represent the expert knowledge, not because they are missing, but because they are vague, right? Ambiguous. It means they are not very clear, right? And then use it whereby such terms, and then use a computer to actually make some sense out of such vague and ambiguous terms in your computer. So what is fuzzy logic? Now, for those of you who are knowledgeable about the term itself, fuzzy, right? If you check your dictionary, fuzzy actually means not clear, right? So why are we studying this fuzzy logic? Are we talking about unclear logic? Right, it's not. So fuzzy logic is not about logic that is fuzzy, unclear, but logic that is used to describe fuzziness. So I can see a main difference here. Fuzzy logic is not to describe the logic that is fuzzy, but using the logic that is used to describe such fuzziness. That is fuzzy logic. So in a way, the fuzzy logic is the theory of fuzzy sets. That's why later on we'll touch a little bit about the fuzzy sets, and that is these sets are used to calibrate vagueness, used to measure vagueness. What does it mean, right? So we're using such things to calibrate, right? Calibrate, basically to calibrate. What do you mean by almost there, on the way, those kind of vague terms, ambiguous terms, to calibrate what do you mean, so that I can use the meaning in my computer program to do some useful computation or useful calculations to solve a problem. Furthermore, fuzzy logic is based on the idea that all things emit of degrees. What does it mean? It means that, for example, temperature, height, speed, distance, beauty, example, all come on a sliding scale. So if you were to expand this, two examples. The motor is running really hot. How hot is hot, right? Really hot. So to me, hot means maybe 100 degrees. And someone said, no, that's not very hot. Hot actually to me is actually must be 200 degrees. So you can see that different people have different appreciation, understanding of even common terms, right? Tom, maybe Christopher is a really tall guy. So how tall is tall, right? So I can see, for example, especially nowadays, if you look at the Olympics, so if you are from the say, for example, certain places, certain countries. So I think recently there was one example. So recently, I think 2 days ago, was it? Oh, no, yesterday. Malaysian doubles team played against these Indonesian players. I think because they are short, they're quite short. They call them minions, and but then they are very powerful. They are, I think, world number top 5 doubles players in the world. So in a country where, I mean, for Asians, I think our average, maybe for Malaysians, our average weight is about maybe 120 pounds, for example, right? So, but if then you go to a different country, a Western country, right? America, for example, where the people are actually, because they are different, they are actually bigger size. So 120 is considered very, what do you call it? Very light, not heavy, not fat, for example, right? So you can see that it's subjective. So again, this one will become clear to you when we actually work and you actually travel a bit to different countries. So you find that, hey, what is considered cheap, what is considered expensive, what is considered tall, short, it all depends, subjective. So those kind of terms, normally you open our eyes and see that, so tall is a very tall guy. So tall means that maybe 7 foot, 7 foot or 7 feet is a really tall guy. But for us in Malaysia, maybe tall can be just 6 feet, right? Because in general, Malaysians are not that tall, right? Again, I know you can also argue when I say not that tall, what do you mean by that? So actually, that's why these ambiguous terms are very tall, really hot, right? So these are things. So what we studied so far is actually based on Boolean logic. So Boolean logic, as you know, uses very sharp distinctions. It forces us to draw a line between members of a class and non-members. So that is one line. I think we said before, I remember reading it in the newspaper, drawing a line to separate the, for example, the rich and the not rich, the smart and the not smart, right? So those are examples. So, but there's a line there. But you find that in many cases, the line itself is actually arbitrary. So for example, here, we say that Tom is tall because his height is 181 cm. Now, if you draw a line at 180 cm, we find that David, who is just 179 cm, is considered small. So you have two classes, tall and small, right? Or tall and short. So as long as you exceed 180 cm, that is your threshold. That will be tall. Anything less than that is small. So I think we have also come across this in the previous years. Students will say, "Sir, I only got 70, but 74.5% or marks, whereas 75 is an A, right? And above is an A. So 74.5, sir, only 0.5 marks. It's so close, I'm almost there. Can I get an A? But the rules says that anything less than 75 is considered B plus and not an A. Right? So that is your Boolean logic. So in this case, David, who is 179 cm, is he really a small man, or have we just arbitrarily draw a line in the sand? That's why it's a very popular saying in English, arbitrary line in the sand. You just draw a line in the sand and say this is this, and anything on this side is, you can draw a line and say on the left of this line is not so smart people, on the right of this line is smart people, right? So this is, questionable. So it's arbitrary. Why you draw it there? Why not shift it to the left, shift to the right, for example? On the other hand, your fuzzy logic reflects how people think, or at least how most people think. So it attempts to model our sense of words. So because of fuzzy logic, it's a way to model our sense of words, our decision making, and also our common sense. It's as a result, right? That this is a bit of marketing. As a result, it is leading to new, more human intelligent systems because it's based on how people think. So how people think and how people, as a result, do things. So if we agree that humans are smart, intelligent, therefore we are building towards more human intelligent systems on this new technology called fuzzy logic. So far so good. Okay. Now fuzzy, or as we said before here, this is a multi-class, no longer just yes or no, black or white, dark or bright. So or this is multi-valued logic, right? So fuzzy or multi-valued logic is no longer just two value, multiple value, was introduced in the 1930s, way back, right? So you can always say that this is as long as maybe as long a history as probability theory by this Polish philosopher. Now, while the classical logic operates with only two values, which is your Boolean, classical logic operates on true or false. But again, the criticism is that it's drawing an arbitrary line in the sand. So this Polish philosopher introduced logic that extended the range of truth values to all real numbers in the interval between 0 and 1. So it's no longer just 2, but all the real numbers, right, in this range of 0 and 1. He used a number in this interval to represent the possibility that a given statement was true or false. Possibility, you look at the word, so this is highlighted. Possibility that a given statement is true or false. For example, the possibility that a man 181 cm is really tall might be set to 186. So now we are given a certain possibility or probability. So you can see here, I'm introducing the probability, which in a way, if you look at it closely, similar to what we talked about before in your uncertainty management and also your Bayesian theory for reasoning. But you can see later as we move along, you see that there's, of course, significant differences. But because of these differences, it actually make fuzzy logic much more powerful and much more relevant, right? Compared to your Bayesian theory or Bayesian reasoning. So because of this 0.86 value, so it is then considered likely that a man is tall. It's not exactly one, maximum is one, so it's only likely that a man is tall. So because of this Polish philosopher's work led to an inexact reasoning technique, right? Based on an inexact reasoning technique, right? So we talk about uncertainty reasoning. Now we talk about inexact reasoning technique, commonly also known as possibility theory, right? Possibility theory based on this. So 7 years later, maybe a few years later, Max Black published a paper called Weakness and Exercise in Logical Analysis. So what else do you see here? So you see here is that that's how technology is being developed. That's how technology is being improved. When you found something new, you need to tell the whole world. So you publish your work, right? So how can you tell the whole world of the new discoveries? So you publish it. So because even nowadays, I don't need to know it now. But once you've documented, I know that such a work has been done, and it's something new, right? So he published a paper in 1937 on logical analysis. So in this paper, Max Black argued that a continuum implies degrees. That means that you continuously from 0 to 1 implies degrees. Same thing, right? Because from 0 to 1, maybe from 0 is not true until 1 is very true. So imagine now, he said that a line of countless chairs. So his example is based on chairs. I think as a simple example. So in the Western world, for example, those are into maybe this kind of art, I'll call it art. One end is Chippendale. There's still one extreme end, Chippendale. It's a chair. Then next to this, notice we use the word here near now. It's very similar to Chippendale or near Chippendale. In fact, indistinguishable from the first item. Indistinguishable. That means that if you look at it, you cannot even say that it's not a Chippendale unless you're really expert. Okay, I can imagine a similar example for us. Maybe we can understand this better. There's been some work. I'm not sure. I think maybe some of you are doing it. Into FIP. I thought I saw this before as a FIP project. I think because your Musang King durian, I'm going back to my durian example again. Your Musang King durian fetches a higher price. I think I saw something, what black thorn, I think from Penang, selling for about more than 100 ringgit per kilogram. So if I can claim my durian is also black thorn, right? I can ask for 100 plus ringgit per kilogram. Compared to, I saw in KL at least, I saw also in Ipoh, in the newspaper, that maybe your D24 durian is selling for something like 14 ringgit a kilo compared to 100 plus ringgit. So what kind of price do you want if you're a durian seller? Of course, I want to claim that my durian is also black thorn. I can ask for 100 plus ringgit per kilogram compared to 14 ringgit. But then you as a customer, can you determine this is a D24 or this is a black thorn, right? So maybe you know a little bit about black thorn. So you say, oh, it looks like a black thorn, but that's why it could be near a black thorn, may not be a black thorn. So how can you differentiate that? So what is the probability? What's the possibility that this is a black thorn and not a black thorn? So here, this Max Black, he used an example of chairs compared to my example of durians. So the near Chippendale or near black thorn is similar to your Chippendale, or near, in my case, is the black thorn. Now, of course, if you move to the left-hand side, as you go down further and further, which is actually you have chairs which are less and less chair-like. Right? You can have a chair because you come back to the definition of a chair. What's a chair? Something for you to sit. So on the other end of the line, it can be just a piece of log, a tree stump. Right? You can still sit, but it doesn't look like anything that tells you it's a chair. But you can still sit, so that will be on the other side, right? Ends with a log. So now question is, when does your chair become a log? When does your chair become a log? But it's still a chair. So Max Black declared that if a continuum is discrete, right? You still have discrete continuums, a number can be allocated to each element, as you'll see in the next slide. Furthermore, he accepted that weightness is a matter of probability. Right, so it is still not very clear, but it's still quite vague, but it's a matter of probability, as you see later on. In 1965, Professor Lotfi Zadeh published his famous paper called fuzzy sets. So I think if you study fuzzy logic, you cannot run away from his name, Professor Lotfi Zadeh. He's a Persian, or nowadays we call him Iranian. He's from Iran. But the thing has spent many years. I think he has not. He's I think probably American now, and he's stayed in America and also lecture and do research in America. So he extended the work of the earlier possibility theory, as we said before, in this Polish philosopher, right? On this possibility theory, extended the work. So that's how you proceed. You extend the work. He extended the work on the possibility theory into a formal system of mathematical logic and introduced, so has two contributions. He extended the possibility theory into a formal system of mathematical logic and then introduced a new concept of applying natural language terms that you and I can actually understand, right? This new logic to represent and to also manipulate because of this processing, such fuzzy terms was called fuzzy logic. And then Zadeh, Lotfi Zadeh, become the master of fuzzy logic, and it become across some books call him the father of fuzzy logic. Now, why fuzzy? Why fuzzy? As we said, as we started off in a few slides before, the term itself, fuzzy, is concrete, immediate, and descriptive. We all know what it means. So his argument is that many people in the world, in the West, were repelled, were were not too happy with the word fuzzy, because it is usually used in a negative sense, right? Because means that you are not clear, right? You cannot tell me exactly, right? Where are you now? I'm near to Taman Bunga Raya, right? So I think some people are not too happy with the way this was used, because it's I'm near to Taman Bunga Raya. I'm near to IUC campus, right? So it's in that negative sense, right? So of course that's why he pointed out. So in a way, at that time when he proposed this method of fuzzy logic, I think he has to convince the West that his method actually is useful and also powerful. So fuzzy is vague, ambiguous, but logic. Now, why you combine logic? Now, what is logic? Logic, basically, fuzziness rests on fuzzy set theory, and fuzzy logic is just one small part of that theory, of your fuzzy set theory, right? So it's still logic, logical or logic. Now, fuzzy logic as a result is a set of mathematical principles for knowledge representation. That's what we're trying to do so far. We're trying to represent knowledge of the expert. In such a system, you still need to rely back on your expert to tell you what are the rules what are the important knowledge you can capture. But this is based on, this is newer, based on degrees of membership. So this is a new term here, something new. You must pay attention. Unlike the earlier ones, your uncertainty theorem, theory, and your certainty factors, and your Bayesian. This is now based on degrees of membership, not based on your probability. Neither is it based on your certainty factors. This is based on degrees of membership, and things become clearer as we go along. When we compare this against your two-value, what they call scripts, or two-value Boolean logic, yes or no, on or off, black or white, right, dark or bright. So fuzzy logic is multiple value or multi-value. It deals with degrees of membership and degrees of truth. So almost similar again to what we studied so far, on the earlier two chapters, two topics. Fuzzy logic uses the continuum, right? Continuous values of logical values between 0, completely false, and if you get 0, completely false, right? And then completely true is 1. So in between is continuous. So it's no longer just 0.5 or whatever. So there's no longer an arbitrary line on the in the sand. So we use all the values in between 0 and 1. So for example, instead of just black and white, it employs a spectrum of colors now between black and white. Accepting things can be partly true and partly false at the same time. Does that make sense to you? So the information, right, can both be right and wrong, depending on how you look at it, right? So as you see later on. So can I maybe go back to our chair example, the Chippendale chair, right? So
Cannot,
if
sir.
we use,
Cannot.
what is it?
Cannot you go back? I'm just kidding.
I got shocked from it. Never mind, okay. You can see a person. You pull a fast one. So back to my Chippendale. So the actual chair that you showed to me has some what I call, can be both a Chippendale and can be something else. Maybe I'll give a better example. A durian now can be 0.6% belonging to D24 and also be another 0.2 probability belong to a kampong durian. So can be both right and wrong, right? This is what it basically means. Right? So partly true and partly false at the same time. So this is what you call by the degrees of membership and degrees of truth. So it's no longer just true or false. You can see here. So this is a good way of explaining it in a graphical form of a picture. On the left-hand side, just a refresher for most of you, right? We always say that between 0 and 0.4, if your output of your normalized output of your system is less than 0.4. Normalized output of your system is less than 0.4 is considered a low. Anything above 0.6, again normalizer, is anything above that between 0.6 and 1 is considered a high or an on. In between here is unknown. So if your output is 24 volts, you normalize it, right? The maximum is say 25 volts. So 24 out of 25 will be close to 1. So that's output 1, logic 1, compared to logic 0. Right, so this is your classical Boolean logic. On, off, black, black, white, what else? Bright or dark. In between is unknown. So you can have only on two values. That's why I call it Boolean. Multiple value logic, no such thing. There's no discrete threshold. every value stands on its own, as you can see here. So fuzzy sets now. Let's move a little bit backwards and then go look at studies fuzzy sets. So it's a quick detour to look at your fuzzy sets. Now, the concept of a set is fundamental to mathematics. I believe you all studied this in your secondary school, a little bit about fuzzy sets, set theory. So this is purely mathematics. Now, our own language, when you say own language, I think this applies for all languages. It's also the supreme expression of sets. What do you mean by that? It means that, for example, a car indicates a set of cars. That means it's a family of cars. I have a car, right? I have a car. You have a car. So then this question is, what kind of car do you have? I have a Polo Duo. I have a Toyota. Then the next one will be subset of that. A subset will be what kind of Toyota cars you have. I have wheels. I have blah blah blah. Right. So you can see that. So basically, it's a set of cars, and then from there, subset and subset and so on and so forth. So when we say a car, we mean one out of a set of cars. So the Boolean logic is based on what we call Crisp set theory. That is, this set theory is governed by a logic that uses one of only two values, true or false, black or white, on or off. So this logic cannot represent vague concepts, ambiguous concepts, and therefore fails to give you the answers on the paradoxes, conflicting concepts. Paradoxes means it is both on and off, right? And I think some students find this difficult to understand, especially if we don't pay attention, because these are paradoxes, both true and false. I can be both smart, I can be both stupid at the same time. That it doesn't make any sense. So the basic idea of the fuzzy set theory is that an element, your element, for example, back to our example of a car, belongs to a fuzzy set with a certain degree of membership. So it belongs to that. Correct. So, Chung-Yi, does that mean that you are smart or otherwise? So you can see, actually, that's why we actually, as a result of that, we never say that we are smart, because it's we can be, I won't say smart, we can be good at one area, but weak at the other area. So that's one of those things. As you see later on, I think you become very, very clear. So the good news is that I would say 80% of the students that have been teaching for the past 6 years in this paper, 2 times a year, make 2 batches a year, find that fuzzy theory, fuzzy sets is actually very simple. They can do quite well. I think it's quite easy to follow. So especially if you pay a little bit, put in some effort to understand the theory behind it and do some calculations, I find that they do pretty well. Right? And so that's the good news. So the basic idea is that the element belongs to a fuzzy set with a certain degree of membership. So therefore, a proposition is not either true or false. So am I smart? Am I good in? Am I good? So I can be a good student because of course, then again, some of you actually are pretty, I will call having superpowers. That means you are good in all papers. I will call those people, I will call them who can actually walk on water, because you score basically, I come across a few in the past few years that your CGPA is almost, it's actually 4. I call him or her actually walk on water, because every paper, the guy has actually done very well. So that is, so that is a really excellent result. So in this case, a proposition is not either true or false, because this is on your crypt. So, but for the fuzzy, it's no longer just true or false, but maybe partly true or partly false to any degree, as you see later on. So this degree is usually taken as a real number in the interval 0 and 1. So in this case, we still, no, I'm sorry, don't see, I'm not one of those walking in water. I'm hardly there. I learn only by doing. So I'm not very good at memorizing things. So, I'm amazed at some of you guys. Almost 4.0 CGPA. I mean, in a way, you find that this is actually you just have to be a bit disciplined. Make sure you just have to discipline and try to learn, basically. But one thing I enjoy learning is technology, so that's why in that way, so it's okay. But again, I think drowning is okay lah. You find that after a while, you will learn how to swim. So it's all right, right? And I'm quite happy to find that one of my student, FIP student, is doing very well. I'll talk to you later on a bit on this. For those of you who are graduating and looking for a job, please sign up. Consider Great Tech, because that student of mine actually is doing very well, because the Great Tech sent him to US for about a few weeks at a time, and is flying off to US this Monday. I think because Great Tech sells equipment to Americans, so the equipment has been commissioned. So he has to send him there to actually commission the machine. So he's enjoying himself. He tell me he enjoy eating the meat, the roast meat over there. Because he said the McDonald's over there is the same as the McDonald's over here. So of course we also joke about this. Yes, the McDonald's over there is the same as McDonald's here, but you pay 4 times the price because of the exchange rate. So he said, forget it, I won't pay 40 ringgit for a McD, Big Mac, or let's say 4 ringgit for a cup of Coke, because that's how you pay, how much you pay. So back to this, back to reality. So this is a this is a classical example of a fuzzy set of tall men. So this is tall. So we know that these are the tall. Sorry, the ladies in the class. It's not my fault. I just copy here. So this one I should change the tall person. But they're all male. Too bad. I think the books itself actually looking at the tall man. So apply to this tall. In a way, it's correct, because normally, biologically speaking, men are taller than women. So women are normally smaller size. Even within that, of course, you can also say that the Americans women are taller than many Malaysian men. Of course, that's different because they are Masale and we are Asians. So the elements of the fuzzy set tall men. So this is a fuzzy set called tall men are all men, right? So the fuzzy set, the elements of the tall men are, first of all, must be men, right? But their degree of membership depends on the height, right? As you see later on. So here you can see what you see here. So you have 3, 3, 3, 10. 10 person here, male, right? And these are the height in cm. So on the left, on the third column here, you can see that I think going back to our earlier example, that 180 is your line in the sand. Anything above 180 cm is considered tall. Anything below that is not tall. I won't say short, still quite tall, 179 cm. So you can see here, if I use that Boolean set, right, I will be having just 2, either 1 or 0. So 0 means that you're not tall, 1 means you are tall in this example. Now, if you look at the last column here, right, you see that it's a sliding scale now, no longer just 0 or 1. So anything above 180, it goes up, maximum of 1, which is close to 205. And I think above 205 is considered tall. Definitely your membership is very high. So think of it in terms of membership. How strong is the membership to that particular class? So in this case, anything above 205 is considered 1.0 excellent. It's like your CGPA of 4, right? So if your CGPA is 3.9, 3.8 is considered smart. So almost can walk on water. So I call it walk on water, and it's a 1.0 membership. So as you go down, you can see there's a sliding scale. Of course, poor Peter down here, 152 cm, is considered not tall, which is actually 0 membership, belonging to that group of tall people, tall men. Follow so far? Now, if you were to draw it again, if you were to visualize this two sets, you have your top one is your crib set or your Boolean set. See here 180 is applying here. So anything below here is actually membership is 0. Anything above here is membership is 1. So you can see it, but on compared to the fuzzy sets, there's basically what I call this sort of non-linear scale, sliding scale increasing. So if your height is here, right? So you measure what's the membership based on this. So it's 0.8 over here, 180. So at every point here, there's a certain level of membership, right? As seen here. This one, later on, you'll find that this is a classical example, what we call the sigmoid graph. A lot very commonly used in your artificial neural network, your sigmoid graph. The x-axis here, or here, right? And see here, represent the height, whereas the y-axis represents your membership. Your x-axis represents the universe of discourse. So your x-axis, this height, right, is called your universe of discourse, a new term. And what does it mean? It means that it combines, it actually looks at the range of all possible values applicable to a chosen variable. In this case, is the height of the person. The universe of discourse is the range of all possible values applicable to a chosen variable. So in our case, the variable is the person's height. So according to this representation, the universe of discourse, universe of man's height, right? This is your universe discourse consists of all tall men, right? So this is a tall man. So so this one will be, we say that John is a tall man with a membership of 0.98. David is a tall man, membership of 0.78. Mike is a tall membership, has a membership of is a tall man, membership of 0.24, and goes on. The y-axis, on the other hand, represents the membership value of the fuzzy sets. So this is your membership value. So in our case, the fuzzy set of tall men maps the height values into corresponding membership values. So you can see here, the y axis maps this, give you this membership. Based on your height, this is a membership of tall man. That's what it means basically. Boundaries, right? So it's not fuzzy. Actually, what it means is that it's no longer cribs. There's a clear threshold. So it's actually continuous, right? And in the classical, the elements will be denoted by X. So the capital X is a universe of discourse, and the elements of X will be lowercase x. In the classical set theory, which is a cribs theory on Boolean, the set A of X is defined as a function f(a)x, called the characteristic function of A. Right, this one is just for your information. Don't want to worry about memorizing it. So in this case, your f of A, the function of X will be X into mapping into 0 and 1, where this is your Boolean. So if X is a member of belongs to the set A, and it's a 1 membership, otherwise it's 0. So this set maps the universe X to a set of 2 elements. This is 1 or 0. So for any element X, any element, so in this case, Tom, John, David, so on and so forth, the characteristic function, this characteristic function f underscore A of X is equal to 1. If X, the element inside this vector, X is an element of the set A, belongs to tall man, as equal to 0 if X is not an element of A. So so it's not belonging to the set of tall men. So in this case, our example here, so you can see that only Tom, John, Mark, and Chris belongs to this set of tall men. Okay. So in the fuzzy theory, the fuzzy set A of universe X is defined by the function R. This is on the first one is called on the cribs, which is a Boolean. remember this word, Chris set A. Now, second one is actually based on the fuzzy. So in the fuzzy theory, the fuzzy A of universe X, right, is still based on the universe X, which is the height of the person, is defined by a function now mu A of X, not F, right? So this one we normally call it mu A, which is called the membership function of set A. Now, membership function of set A still maps into 0 and 1. All the members of all the individual elements of X still map into 0 and 1, between 0 and 1, where your mu A equals to 1 if X is totally in A, which is your 4 cases, your John and your David and your Tom, your John, your Mark, and your Chris, all into, sorry, you do these two, just one, Chris and Mark. Right, totally in A is 1. Now, the membership function set of A, mu A x equals to 0 if A x is not in A. So that element is not in A. In between is can be any value between 0 and 1. It's partly in A. So as a result of this set allows a continuum of possible choices. And for any element x of universe X, the membership function mu A equals to the degree in which X is an element of set A. So this degree or value between 0 and 1 represents the degree of membership, also called the membership value of the element X in the set A. Okay. First, how do we represent a fuzzy set, right? This fuzzy set in a computer, because we are still trying to look at developing using this theory to build an intelligent system in a computer. So firstly, we will have to determine the membership functions, right? So in our example, we can obtain, in our example of tall man, we can obtain fuzzy sets of tall, short, and average. So we arbitrarily say I want only 3 fuzzy sets of tall, short, and average. So the universe of discourse, the man's height, right, then consists of 3 sets: the short, average, and tall man. Tall, short, average. As you will see, a man who is 184 cm tall is a member of average man, set with a degree of membership between 0 and 1. And at the same time, he can also be a member of the tall man set with a degree of 0.4. Right? So in the case, if you use the Cripps set, I would then say that this is actually an arbitrary set. We just set 170. Anything below that is considered short. Anything between 170 and 180 is considered average, and anything above 180 is considered tall. This is a Cripps set. So if your value is here, right, I'm only short, right? 1.0 membership. Same goes for average and tall. Finally, the other one. Now, the other one is a fuzzy, right? For fuzzy, again, I will define as short, average, and tall. So here, if my height is 184 cm, what do you see here? My membership for average is 0.1. At the same time, I also belong to the group of tall men, membership 0.4. So I belong to both groups. Okay. Okay, I think we stop here. Christopher, good question. No, it's not so simple as that. If you average out, it's not so simple. Later on, we will see. So it's actually quite a nice way of getting a result. It's not so simple as just averaging it, right? You will see later on. Okay, so I think let's stop here, and then we continue on next week. So next week we have labs on Monday and Tuesday. And then we have back to your so for those of you who have not found your members for your teammates, quickly find them. I think okay, maybe I have not checked yet. I think I mostly remembered, I think, request by Christopher, I think a few days ago, that maybe, no, I think, is it too early for me to discuss the, no, I think it's still too early. Maybe I'll do it next week. Not this week one. Maybe middle of August, I will maybe talk about the assignment briefing. I'm thinking now if okay, question is, do you guys have anything on Wednesday morning between 9 and 10 before our class, before our lecture? If not, I'm thinking now, can we have okay, maybe because I think the deadline for the assignment is, I think, somewhere August, right? So I think maybe, can we have come in early at 9 o'clock Wednesday morning? Right? No more. Okay, good. Because I just want to. Okay, tell you what. I will confirm it later on. Please check your check your email. I will send out a notice for you to come in to earlier. I'll discuss about the assignment. Maybe 40% of that contents may not be, you may not understand, because you need to complete this lecture first. But again, it's a good start, so that at least you have a head start to try thinking about what you want to do for your, how you want to do it for your assignment. So tentatively, I will have a early briefing on your assignment on Wednesday morning, 9 to 10, at this same Google link. But I will confirm again by sending out an official announcement. Okay. So before we stop here, before I end the class, any questions from anybody? If not, enjoy your weekend, and I'll see you next week. Bye-bye. David, we have a meeting here or elsewhere? Okay, let's wait for, or you want to wait for the class to leave first, David?
Sir?
Yep.
If I'm not mistaken, based on my apps, right, tomorrow have replacement, right?
Oh, no. That one is actually, I got that's mock. I think it's not, it's a tutorial, which most of you attended either on the Tuesday or the Thursday. So it's all done.
Oh, so
It's just for recording purposes.
wait, so tomorrow one, do we need to attend, sir?
Have you attended the tutorial yet on search?
Search, wait, let me check.
Tutorial 2. Because I think I asked you all, and then you all said that you don't want to have a actual another, what do I call it, extra. You just join the other classmates in their Tuesday or the Thursday tutorial sessions, and I see that some of you have done it. So but I need this for the EAC, for the official purposes, so that it's separate, right? So you don't have to.
So actually, that one is just put there.
For me to just show that there's a replace. Actually, you replace already. You join the other groups, easier for you.
Okay. I join group 2 lah. Okay. Thank you, sir.
MH, yeah, MH, isn't it? MH,
yeah, IMH.
I think your what you call your tutorials on Tuesday, am I correct?
Yes.
No. Tuesday, okay.
Wait, let me check. Let me check.
I think 12:30. There's one more 8 to 9, and one more is I think.
Yeah, Tuesday 12 to 12:30 to 1:30.
Correct. Correct. Okay, just join that, easier for you. You don't want to come back. I think most of you don't want to come back on a separate day.
Okay. Thank you, sir.
Okay, bye-bye.
Thanks.
So anything else? David, you want to do it here or elsewhere? Maybe, oh yeah, okay. Okay, sure. I think I need to find the link. Okay, the rest of you, nothing. Bye-bye. Yes.
Yeah,
Yes.
Tia here. I'm from
Yes.
LE. Yeah,
Yes.
I want to clarify something about assignment group before because for my course we have a 48 student. So I have no idea why
left? It's 49 because your official class is 50. Your officially, I got the numbers is 50.
Okay.
And there's one of you actually have joined another course, so it's 49.
Yeah, I think the student is Jingwen. He joined he's RTE, so he's not taking this this subject.
Oh, no. There's what was it? On something. On
Kai Chen, is it?
On Kai Chen actually is joined the thing. Com science, is it?
Com science.
So, I don't know, but I know there's, from what I have, 50, you know. So minus one is I can see, I will check attendance, it's 49. So that one has this student has left.
Oh, okay. So it's correct one. So it's just 49 student.
Is it correct? 49? Is it correct? Mine is 49.
Because the list that I have currently is 48.
Do you know who's the two person who's not here? Would you know? Don't know.
No, I think I need to check first. Then I do a confirmation again. Okay.
I know. Okay, Jia, I will reply you to I will reply you to WhatsApp. That one is
okay. Sure.
A bit sensitive.
Okay, all right. Sure. Sure. Yeah.
Okay. I will send to you the list that I know. You confirm against your list.
Okay, all right. Sure.
And then I think is it
because
actually
one
RTE.
Because actually still got people that who haven't have the group yet, and the name is not posted in the
correct.
Google Classroom yet. Okay, right.
Oh, what's that one? Because I compare the one who signed up Google form against my master list, and those are the names I don't have. Well, who doesn't seem to have the names.
Because
the rest have members already.
Because he say he don't have group and he not yet fill up the form and his name is not in the Google Classroom there.
Who is here? Is it sensitive?
Maybe I WhatsApp. Maybe I do a confirmation first. Then Okay, right. Thank you, sir.
Okay, final check. Anyone? Anything else? If not, bye-bye. Have a nice weekend. I'll leave now.